So what is an eigenvalue exactly? Well, I think it's important to orient ourselves appropriately before stating a mathematical definition. So an eigenvalue is a scalar value that we associate to a square matrix. So whenever we're discussing eigenvalues, we're always discussing square matrices. So a 3 by 5 matrix cannot have an eigenvalue, but a 7 by 7 matrix can have an eigenvalue. When a matrix does have an eigenvalue, so when a matrix is square, the eigenvalues are scalar quantities. So what are these scalar quantities? We say that a number lambda is an eigenvalue of a matrix A if this difference matrix, A minus lambda times the identity, is a singular matrix. So let's repeat this definition. We say that a scalar value lambda is an eigenvalue of a matrix A if this difference matrix, A minus lambda times the identity, is a singular matrix. Now, think about everything we know about singular and non-singular matrices. For a matrix to be singular, it needs to be a square matrix that does not have full rank, which also means that that matrix does not have an inverse. So if we're looking for an eigenvalue of a matrix A, what we want to be doing is we want to be looking for numbers lambda that we can plug into this difference matrix, A minus lambda times the identity, so that the result is a matrix that does not have rank equal to n. So we can state that this is our first theorem. Lambda is an eigenvalue of A if and only if the rank of this difference matrix, A minus lambda times the identity, is less than n. This theorem gives us a test. If someone hands us a matrix A and someone hands us a number lambda, and we want to know whether or not lambda is an eigenvalue of A, well, all we need to do is look at this difference matrix, A minus lambda times the identity, and verify whether or not the rank is less than n. Also, one of the things we know from this theorem is that if someone hands us a matrix A, and if someone hands us a number lambda, and they tell us that lambda is an eigenvalue, then we automatically know that the rank of this difference matrix is less than the size of the matrix. So let's see an example. So here we have a 2 by 2 matrix whose numbers are, or whose entries in the first column are negative 63 and negative 20. And then in the second column is 240, 77. So if we want to check whether or not a given number lambda is an eigenvalue of this matrix, we need to calculate the rank of the difference A minus lambda times the 2 by 2 identity. So here what we have is a calculation where we're considering the difference between the matrix A and negative 3 times the 2 by 2 identity. So if we take our matrix A and we subtract negative 3 times the 2 by 2 identity matrix, we produce this new matrix. And this new matrix is a 2 by 2 matrix whose columns are negative 60, negative 20, and then the second column is 240, 80. So to address the question of whether or not negative 3 is an eigenvalue of A, we want to know whether or not the rank of this difference matrix is less than 2. Now, when matrices are small enough, sometimes we can just tell what the rank is right away. For this difference matrix, since it's 2 by 2, the only possible ranks are 0, 1, or 2. This is certainly not a rank 0 matrix because the only rank 0 matrix is the matrix with all zeros in it. Now the question is whether or not it's rank 1 or rank 2. And one thing to note here is that if I multiply the first column of this matrix by negative 4, I produce the second column of this matrix. So that means that the two columns are linearly dependent, which tells me that this matrix is singular. So right away, I know that the rank of this difference matrix, because I can scale the first column to get the second column, is 1. Here's another calculation. Here we're taking A and we're subtracting 7 times the identity matrix. That difference matrix has columns negative 70, negative 20, and then 240, 70. We can look at the rank of this difference matrix, And the rank of this difference matrix turns out to be 2. So it's not possible to scale the first column of this difference matrix to produce the second column. So the rank of this difference matrix is 2, whereas the rank of our first difference matrix is 1. What can we conclude from these calculations? Well, because the rank of A minus -3 times the identity is not equal to 2, we know that lambda equals -3 is an eigenvalue of A. But since the difference matrix A minus 7 times the identity has rank equal to 2, we know that lambda equals 7 is not an eigenvalue of A. So if we want to check whether or not a number is an eigenvalue of a matrix, we look at A, the matrix, minus lambda, the number, times the identity, and we check whether or not that difference matrix has full rank. Here we have a 3x3 example. So here we're taking a 3x3 matrix called A. We're subtracting off 14 times the identity matrix, and that produces this new 3x3 matrix. Well, one thing we know here is that the rank of this difference matrix is definitely not equal to 0 because this matrix has entries in it other than 0. We also know this is not a rank 1 matrix because in a rank 1 matrix, every single column is a multiple of every single other column. And we can quickly see that the columns aren't all multiples of each other for this particular example because in order to get like the third column to be a multiple of the second, for example, we would have to get from -3 to -3, we'd have to multiply by 1, but 1 times -4 is certainly not -14. So we know that the rank isn't equal to 1. So the only other options are rank 2 or rank 3. And so the only possible rank of A minus 14 times the identity here is 2 or 3. And that's as far as I can get immediately by just looking at it. I think, however, to sort out whether or not the rank is 2 or 3, I need to do some calculations. So I went ahead and row reduced the entire A minus 14 times the identity matrix, and I got the identity matrix, the 3x3 identity matrix. This tells me that the rank of my difference matrix is equal to 3, not 2, which tells me that lambda equals 14 in this case is not an eigenvalue of A. So to recap, we took our original matrix A, we subtracted off 14 times the identity matrix, and we found that the result was a matrix that had full rank. This is a non-singular matrix. Because this difference matrix is non-singular, that tells me that the number 14 is not an eigenvalue of my matrix. Okay, so eigenvalues are very powerful tools for understanding the structure of a matrix. So let's right now just state a few things we can say immediately given the definition of an eigenvalue. So let's say that someone tells us that lambda equals 0 is an eigenvalue of a given matrix A. The question is whether or not we can say anything interesting about A. Well, if we think about it, remember that A is really the same thing as A minus 0 times the identity. And if someone is telling us that lambda equals 0 is an eigenvalue, what that really means is that A minus 0 times the identity is a singular matrix. So that's telling us that saying whether or not a matrix itself is singular is the same thing as saying whether or not lambda equals 0 is an eigenvalue of that matrix. So we can add this to our list of ways to categorize singular matrices. We saw in our previous lecture that one way to check whether or not a matrix is singular is to verify that its determinant is equal to 0. Now we have another way of verifying whether or not a matrix is singular. Namely, if we could look for all the eigenvalues and check whether or not lambda equals 0 is one of them. So let's state this as a theorem. A matrix A is singular if and only if lambda equals 0 is an eigenvalue of that matrix. An equivalent way of saying this is to say that a matrix A is non-singular if and only if lambda equals 0 is not an eigenvalue of our matrix. So if someone gives us a matrix and they give us a list of all of its eigenvalues and 0 is not on that list, we know immediately that the matrix we're interested in is a non-singular matrix. So here's an example. So this matrix is 2 by 2, and we're told that it has rank 1. This matrix is small enough that we can verify that assertion ourselves. One thing to notice is that if we scale the first column here by -3, we produce the second column. So these two columns are not the zero vector, but if I scale the first column by a number, I get the second column. So this matrix has to have rank 1. Well, a rank 1 matrix that's a 2 by 2 matrix is an example of a singular matrix, because the 2 by 2 non-singular matrices are exactly the rank 2 matrices. So once I know this matrix is singular, I know immediately that lambda equals 0 is an eigenvalue of this matrix. Now, I can verify whether or not other numbers are eigenvalues of this particular matrix. So here, let's subtract off -2 times the identity from this particular matrix. When we do that, we produce this new matrix whose columns are -6, -2, 24, 8. And one thing to note here is that if I scale the first column of this new difference matrix by -4, I produce the second column. So the rank of this difference matrix is also equal to 1. This tells me that lambda equals -2 is also an eigenvalue of our original matrix, and so was lambda equals 0. So this example verifies or illustrates the fact that one matrix might have multiple different eigenvalues. Here's another example. So here we're looking at an upper triangular matrix called A. And this is the matrix whose diagonal consists of the numbers -3, 17. The number above the diagonal is -4, and then the number below the diagonal is 0. Let's say that we were looking for eigenvalues of this matrix. Well, what we would want to do is we'd want to look at the generic difference between A and lambda times the identity, where lambda is unknown here. And when we subtract off lambda times the identity from this upper triangular matrix, we produce a new upper triangular matrix where the diagonal entries are -3 minus lambda and 17 minus lambda. Now, if we're looking for lambdas we can plug into this matrix that verify that lambda is an eigenvalue of A, then what we're really trying to do is force this difference matrix to have rank less than 2. And if we stare at the diagonal entries here, we realize all we're really trying to do are find the lambdas that we could plug in that would prevent a pivot from occurring in one of these two diagonal entries. So if we focus on the 1, 1 position of this difference matrix, we're looking at -3 minus lambda. Well, and also if we look at the second position on the diagonal, we're looking at 17 minus lambda. Well, one thing to notice is that if we plugged in lambda equals -3, that would zero out this 1, 1 position, and the resulting rank would be equal to 1. Another thing to notice is that if we plugged in lambda equals 17, that would zero out this second diagonal position and force this difference matrix to also have rank 1. So this is showing us that both lambda equals -3 and lambda equals 17 are eigenvalues of our original upper triangular matrix. And this is an interesting calculation for us because -3 and 17 are the diagonal entries of our upper triangular matrix that we've started with. So one thing to learn from this example is that for this upper triangular matrix, the eigenvalues were exactly the diagonal entries. So let's state this as a theorem. The diagonal entries of a triangular matrix are the eigenvalues of that matrix. So if we're working with an upper triangular matrix, it is not difficult to find the eigenvalues. We simply pluck out the diagonal entries. So here we have a rather large matrix. This is a pretty nasty 5 by 5 matrix. But it's not that nasty because this is an example of a lower triangular matrix. Every entry above the diagonal here is equal to 0. Well, because this is a lower triangular matrix, I know that the eigenvalues are sitting on the diagonal of this matrix. So the eigenvalues are the numbers negative 148, 16, 57, 7, and then negative 148 has already been listed, so I don't need to list it again. So this matrix has eigenvalues equal to 16, 57, negative 148, and 7, because those are the diagonal entries of this matrix. Let's look at other types of problems we can solve with eigenvalues. So let's say that we know all of the eigenvalues of a matrix A, but now we want to study a new matrix, A plus a scalar multiple C of the identity matrix. Well, how would we go about tackling this problem? Well, we would want to start with the definition of an eigenvalue. By definition, lambda is an eigenvalue of some matrix if the difference between that matrix and lambda times the identity is a singular matrix. So what we really want to do is we want to start with the matrix we're interested in here, and the matrix we're interested in here is A plus C times the identity. So we take A plus C times the identity, and then we subtract off lambda times the identity. We can rearrange our parentheses here and distribute, and we realize that we're really looking at A minus the quantity lambda minus C times the identity matrix. So now the question is, if we have freedom to choose lambda here, what is the appropriate lambda to plug in to force this entire matrix to be singular? Well, this occurs exactly when lambda minus C is an eigenvalue of the original matrix A. So we can state this as a theorem. The eigenvalues of A plus a scalar multiple C of the identity are the same thing as the eigenvalues of A shifted by a factor of C. So here we have two matrices. We have this matrix A, which is 2 by 2 and filled with all ones. And then we have this matrix B, which is 2 by 2. The first column is 0, 1, and the second column is 1, 0. Well, let's say that someone tells us that the eigenvalues of A are the numbers 0 and 2. Well, the question is whether or not we can use this information to conclude anything about the eigenvalues of the matrix B. Well, one thing to note here is that B in this example is really A minus the identity matrix. Note that A has ones in the upper right-hand and bottom left-hand corners of its entries, but zeros on the diagonal, or but ones on the diagonal. We can get to B by subtracting off these ones from the diagonal. So really, B is of the form A minus the identity. So what this is saying is that if we want to find the eigenvalues of B, we simply subtract 1 from the eigenvalues of A. So since the eigenvalues of A are 0 and 2, the eigenvalues of B are negative 1 and 1.